Let's design a video sharing platform. All the components and the design we will be discussing in this video, most of it can be plugged to any video sharing platform, say YouTube, Netflix, etc. As usual, let's see the requirement gathering. So we will have a discussion with the interviewer. Couple of requirements we'll try to finalize, and so which we can discuss in the overall interview. Couple of requirements which are very frequently discussed and are quite popular for a video sharing platform: able to upload video content and view or stream videos. So two things: ability to upload the video content and stream videos, like, comment, etc. on a video. All these features related to like, comment on a video, this is already covered in quite a depth in designing a scalable feed system. There we covered it, of the like, comment and all that sort of stuff on a post. Similar can be applied and plugged it here for a video as well. Daily active users, let's consider it to be 5 million, and it can scale further if product becomes a lot more famous. Need to support good number of formats and resolution so that videos can be viewed on phone and web. Also, videos can be streamed in both low and high internet speeds. So this is quite an important feature which we need to keep in our mind, that it's not like that the user is uploading in a certain format and resolution and we only have to keep it that way. We need to provide that video in multiple famous formats and resolutions, depending as the people who are streaming it can be streaming it via their mobile, via web, TV, etc. All these appliances supporting different formats and resolutions, and they can be under high or low internet speed. So based on that, we need to discuss these formats and resolutions, how we will be supporting that. Support for some generic things: stream videos smoothly in both high and low internet speeds. This is an important thing which we need to keep it in mind. Ability to change video quality while viewing or streaming a video, allowing a user, giving the user an ability to stream a video and also change the video quality. So we need to support multiple video qualities, resolutions like 240p, 480p, 720, 1080p, and so on. Make our overall system highly available across multiple locations. It can be that someone who is uploading the video is part of some X location, but people who are streaming videos are from Y location. So we need to make it highly available across multiple locations. Once requirements are finalized, let's move to back of envelope estimations. Let's try to analyze for two of our major flows: uploading video content and viewing or streaming of videos. Let's see the back of envelope estimations from the perspective of uploading videos. As discussed in the requirement gathering process, we have 5 million daily active users. DAU is daily active users. So let's say 10% of user upload one video per day. So we'll have 5 million times 10%, which becomes 0.5 million. Considering an average video size of, let's say, 300 MBs. So 0.5 million times 300 MBs are million gets converted to TB directly. And then 0.5 times 300 becomes 150. So 150 TB per day. So that's quite a good amount of storage that is required to support uploading of the video content by our 10% of users, considering they upload one video per day. So we require 150 TB of storage per day. Now let's see back of envelope estimation on streaming videos. Say each user streams on an average 5 videos per day, and we had 5 million daily active users as we saw above. So 5 million times 5, and on an average, as we considered, we have taken 300 MB on an average for each video. So this becomes 25 million times 300 MB. 300 MB, let's consider it to be 0.3 GB. So 25 million times 0.3 GB becomes 7500 TB or 7.5 petabytes per day. So for this large user base, and considering each user streams 5 videos per day on an average, with a video size of on an average 300 MBs, we would require such a large amount of streaming, which will be around 7,500 TBs per day, which is quite on the large side. And also for uploading the content, we require 150 TBs per day, which is also again on the higher side. Considering this huge scale of data, it would be best if we opt for cloud storage like S3, Google Cloud Storage, etc. These are good to store the video content. So storage of video content, it's best if we move towards cloud storage options and explore that. For our video, for this video, we will consider S3, but yeah, you are free to consider any other cloud storage options and discuss that during the interview as well. And we will use CDN like Cloudflare, Amazon CDN, etc. for streaming all the video content for now. Let's see what will be the costing from a very higher level. So I got this screenshot from Amazon CloudFront CDN. It's mentioned over here as $0.02 over 5 petabytes of streaming content per month from a region, United States, Mexico, and Canada. Let's assume this is our selected region. So say we consider 5 plus petabytes or upwards of streaming. So we will have for our 7,500 TB of video content streaming time 0.02 per GB per month. It will cost our system around $150K per day or $4.5 million per month, which is quite on the very higher side, like costing our system $1,50,000 per day or $150K per day, and going in the costing of millions per month. Although generally for these large scale customers, CDN is good to reduce costs substantially for them. So generally these large scale companies with these large scale systems generally tie up with CDN to lower the cost substantially, but yeah, still it is on the larger side, which we'll see to optimize on a very high level what we have with us currently. Let's discuss that and try to make some design out of it. So we have users, let's say users are uploading the content and streaming the video content from mobile phone and web. So for streaming the videos, we have one flow to do the streaming of videos from CDN, and everything else, including managing of user profile, handling of the metadata of those video content, getting the upload URLs, which we'll discuss just below. And we have also discussed this terminology in our feed system as well, then uploading of videos, etc. All these sort of things. This will go in our second flow of API servers and cloud storage. Now, user will upload a video, say myvideo.mp4. We would need to do computation and encode this video into multiple formats and resolutions based on our use case. As we saw above, that we need to support good number of formats and resolution, so that if a user is uploading a certain video in a certain format, still it can be viewed and streamed by other users supporting present in different formats and resolutions based on their internet speeds as well. So we need to provide a smoother streaming of videos and not any buffering, and avoid like lower down the buffering as much as possible to the video, to the users who are streaming this uploaded video content. So this is what we have discussed over here, that user will upload a video, for example a certain video, and we would need at the backend do computations and encode this video into multiple formats and resolutions. Now this overall process of capturing the video, doing the computations and encoding them into certain formats and resolutions is called video transcoding, or you can also refer as video encoding. So let's see how the video uploading would happen. User X wants to upload the video myvideo.mp4. it will call our API servers. Okay, it will call our API servers and tell the API servers that I want to upload a video. API servers will call the cloud storage, say S3, that a user wants to upload a video. The cloud storage would return a pre-signed URL, which also has some expiration attached to it. And then these API servers will return this pre-signed URL to the user, using which the user will upload the video directly to the cloud storage. All this process of fetching the pre-signed URL and then uploading it using the pre-signed URL from the user side directly to the cloud storage, this has been discussed a bit more in depth in our feed system video. Once video is uploaded on cloud storage, say S3, we would want to reach to a transcoding servers which handle this video and encode it into various formats and resolutions. So it's not the responsibility of user to upload his or her certain video into multiple formats and resolutions. It's our responsibility to do that. So once that video is uploaded to S3, we would try to capture that video content and then move it to our transcoding servers, which handle all this process of encoding it into various formats and resolutions. For this, we can have SQS on our S3 bucket of new object created. So what SQS does? SQS is simple queuing service which will publish object created event having, say, couple of things: event name, bucket, key as the file name, and the video name which just got uploaded with couple of other fields like tags and couple of other things. So on our S3 bucket, once a new object is created, we will try to integrate SQS. So whenever a new object is created, a new video file is uploaded, it will publish an event with couple of fields and video file reference, bucket name, event name, and that sort of stuff, which needs to be consumed by our transcoding servers. Now my transcoding servers will consume these events from SQS or published to SQS, extract the event payload, which has important fields pointing to the video object to specific S3 bucket, right? They will, so our transcoding servers, they will download that video and then start with the encoding process. So let's see a little bit of few popular video formats and resolutions. We don't need to remember these things related to format and resolution, but it's always good if you showcase it a little bit during the interview. So let's say for format and resolutions, we know that we can have 240p, 480, 720, 1080p, etc. Couple of formats we can support, which our transcoding servers will encode the video in. We can have H.264, VP9, HEVC or H.265. So this HEVC, this is used by Netflix, Amazon Prime, etc. VP9 is popular with Chrome and YouTube, and H.264, everyone mostly uses it and can be used as a fallback. All these formats support certain resolutions and then they can be mapped to these resolutions, and our video transcoding server and our transcoding servers can encode our video to these certain formats and resolution pairs. On a high level, higher the resolution, better the video quality, and higher the internet speed is required. That is why we have to encode it somewhat into lower resolutions and higher resolutions as well. We need to support both, because we can have a user who is on a low internet speed. We can have users streaming our video content on a high internet speed. They can be streaming from their phone devices, they can be streaming from their laptops, desktop, etc. Now, once video is encoded into multiple format resolution, it is stored back again to cloud storage. Now, once our transcoding servers have encoded this uploaded video into couple of formats and resolution pairs, we need to upload these encoded videos again back to the cloud storage. And in parallel, We can publish an event notifying that video is transcoded so that the metadata related to all of this can be stored in our database. So that the metadata related to whatever formats and resolutions we encoded the video, where it got stored now on the now on our S3 bucket, the bucket, couple of other tags, the format, video size, and all that sort of stuff, all this metadata then needs to be stored to in our database. So we need to publish an event for that. Let's see our database schema, what we need to store as part of metadata and how it would look like. So in our database schema, I'm not covering user table as it's quite common. You can have user ID, name, email, devices, couple of other things. It's discussed a little bit in a couple of my other videos, so that's fine. It's quite common and similar can be reused here as well. For videos, it will have a video ID to have the uniqueness. Then it will have a owner ID stating which user, having the user ID, which user uploaded this video, video title, video description, all that text information. It will have an overall status of the video. Then it can have couple of other timestamp fields, created at, uploaded at, and couple of other things. Another table which is quite important will be video sources. This will have an ID, video ID, referring to the original video ID. Then we can have bucket reference, which will have the S3 bucket reference, where this video got uploaded on our cloud storage, reference to that. Object key, so path to that video object, video name, file name, path, overall path, and that sort of stuff. Size of the video, format and resolution, timestamp, and couple of other fields. So we can have separate table for our original video, how it got stored on our cloud storage, on our S3 bucket, and a separate table for the encoded video. Or we can combine and store original plus encoded videos together in this table, as we have taken the format, resolution, and the sort of bucket reference in these fields in video sources table itself. We can also define a couple of other tables such as encoding job status tracking, etc. So what's the status of each video's certain format and resolutions encoding jobs status. So we can have a separate table for that, and you can discuss that as well based on which direction the discussion is going during an interview. So let's see high level of uploading video content. So what we have till now, let's see how the design will look like of uploading the video content. So we have users uploading the video content. Their request going via the load balancer went to API servers to get the pre-signed URL. Then using the pre-signed URL, they uploaded the video. So they uploaded video content via the pre-signed URL to our cloud storage, say S3. As soon as the video upload gets completed, it will publish object created event to SQS. So that gets published. And our encoding servers are present to consume these events of object being created from SQS, having all the necessary fields, say S3 bucket, the path to that, name of the video, and couple of other tags related to it, so that our encoding servers can reach out to the cloud storage and start downloading that video which got recently uploaded. So these encoding servers would then start encoding videos, this uploaded video, into specific formats and resolutions which we have configured. And once it is done, it will again upload back the same video in different formats and resolutions again back to the cloud storage. And once that is done, it will in parallel also publish encoding completion event to a message queue stating that I have completed encoding of video in these specific formats and resolutions. So we'll publish this completion event. And then from our message queue, there are our workers which will consume these events, extract out all the metadata, which we just discussed above, having all the video sources, encoding formats, size, resolution, bucket, reference, video name, path, etc., and store all this metadata and other stuff to our database. From a very high level, there will be users who want to stream the content as well. So they will be requesting the CDN to stream the content. Now CDN will have a cache miss or cache hit that we will discuss, that we will deep dive below. And these videos get cached in CDN for streaming from a higher level. The CDN has the source of origin set to these cloud storage or S3 buckets, and it would fetch it and cache it on CDN, and users can stream these videos directly from CDN. That we'll discuss a lot more in detail below. So we have discussed the uploading of video content a lot more in depth. Now let's try to deep dive a bit on individual components. Firstly, let's see on this part that user needs to stream the video content via CDN. So these CDN have edge servers or content delivery networks. These have edge servers present at different locations, right? When a user requests a video of a certain format and resolution, these CDN are configured, right? Users who want to stream the video will request in a certain format and resolution depending upon from which device they are requesting and what type of quality they want based on their internet connection and that sort of stuff. So these CDNs are configured with their source of origin being our cloud storage, say S3 bucket, holding all the video objects. So all the original video objects are present in our S3 bucket, and these CDNs are configured to point to that as the source of origin. Once a user requests to stream video from a certain location, it will get a cache miss on that edge server, right? So user will make a request on the CDN to stream a certain video. It will initially get a cache miss on that edge server. That edge server will pull the video from original source and then cache it. Subsequently, to users requesting to stream the same video will get cache hit on that edge servers. So all the subsequent users will get a cache hit on that particular edge server who will try to now request to stream the same video. This is also called as read-through streaming cache. Here CDN opens up a connection to origin. In case of a cache miss, origin starts sending video segments and not the whole video. So video is sent in video segments, and CDN alongside caching these video segments also directly forward them to the user rather than waiting for all the segments to arrive and get cached and then forwarded to the user. So this is called read-through streaming cache, that the CDN opens up a connection to the source of origin, starts to download the video in segments, which can be of couple of seconds or so, and in parallel caches it and also forwards them directly to the user so that they can start streaming. Let's deep dive now what happens behind the scenes in the encoding process, what was happening in our transcoding server's black box. So in encoding process, we have container, video, audio, metadata, etc. So let's say this is our original video. It will have couple of components: video, audio, and metadata attached to it. Here metadata is directly packed into the container, but the audio first gets encoded and the video separately gets encoded into whatever formats and resolutions we want, and then they all get packaged together into container. The original video is extracted to get raw video, raw audio, and metadata, as we just discussed above. Then these raw video and audio are encoded into different formats. For video, let's say H264, VP9, H265, etc., with their relative resolution mappings. And then eventually they are packaged together based on our streaming protocol defined, like we are using HLS live streaming, MPEG, etc. Let's discuss what will happen on large video uploads. For that, let's say we have a 300, 500, a GB or so of video which we need to upload. We don't want, let's say we have a 300 MB video that we start uploading it. The user starts uploading it to our cloud storage, say S3, and at reaching 250 MB upload, it fails due to any possible reason, maybe internet connection or failure from the cloud storage side or something like that, or drop off connection, right? So for that, we can use S3 multi-part upload. With this, we upload video in multiple parts. Say for our 300 MB video, it will be done as, let's say, part 1 having from 0 to 50 MB, part 2 having 50 to 100 MB, part 3 having 100 to 150 MB, and so on. So during multi-part upload, it sends the part number with couple of e tags along with it, and the cloud storage at its server side assembles them together. Failed parts can be retried for upload. So here we don't have to retry if something breaks the whole video. We just need to upload that, re-upload that failed parts, which are of couple of MBs. Here each part is uploaded independently. And when all are uploaded, it again sends a complete multi-part upload. Only after this, S3 starts to assemble things together at server side. As we just discussed, each part is uploaded independently and can be uploaded in a jumbled way as well. And once everything gets uploaded, S3 will assemble everything together, all these parts together, into the original video at its own side and drop all these parts and will store the original video. Storage in S3, we refer it as blob, which is binary large objects. An S3 object contains bucket, key, which can be path or file name, data bytes, and metadata. So we store our video content file as an S3 object, which is an immutable blob. Here S3, without understanding the file format and other stuff, stores directly based on the bytes and metadata. So all the upload of video content and storage of these original and encoded videos in S3 is known as S3 blob storage. Now let's try to deep dive a bit more on optimizing the storage and CDN costs. As we saw in the back of envelope estimation, our storage and cost of CDN was quite on the higher side. For less popular content and doing analytics over certain content type and region, we can encode it to very limited formats and resolutions. So rather than encoding each and every video to every format and resolution we have configured, based on our analytics and the content, what we can do is, based on analytics, content, and the region and the type of the video that is getting uploaded, we can encode it into very specific formats and resolutions to save storage. We can avoid distributing region-based content to other region edge servers. So not to distribute or avoid distributing a specific region-based content or a specific type of content to other edge servers where it is not even being requested by users to be streamed. Or we can go in the direction of what Netflix did, building their custom CDN, which they called as Open Connect, and partnering it with ISPs. So let's discuss what Netflix did with Open Connect and if the platform is got very popular and the videos that need to be streamed are quite large as well and are streamed at very high scale. So we might need to consider something as what Netflix did with Open Connect. To give out the best quality of experience, so they focused a lot on QoE, quality of experience. They wanted to deal with couple of problems that they were facing: delay in video start times and reduce the initial bufferings. So what they did is they had their custom built servers, which they called as open connect appliances or OCAs, to provide higher efficiency and even reduce their costs. They wanted to analyze and bring localized content as close to the end user as possible, and this to be done globally for all the regions. They wanted to bring the specific content which is popular in certain regions or regional based content as close to the end user as possible to give out the best user quality of experience, and this to be done across all regions globally. What they did is they partnered with all the ISPs like Comcast, Verizon, Airtel, etc., to physically install their custom servers inside their ISP networks with lots of content getting cached important to that local region. This gave lesser network hops, lower latency to stream content, and solve their problems which they faced with all content being served from the third party CDNs. These open connect appliances or OCAs, they cached popular content, regional content, etc., based on all the analytics they did, and not all the content which is out there. So all these OCAs, what they did is they installed it by partnering it with the ISPs, and it cached all the popular content and the regional content which is famous in a certain region, so that the user can get the best possible experience with lesser network hops and lesser latency, improving the overall quality of experience. So this I get from their Netflix article which they published over Medium. So they configured this sort of stuff. What they mention is that they have their OCAs installed by partnering it with ISPs, and they have their cache control service. These OCAs report health status, routability, and all the available files that are cached on them to cache control service. So whenever the users from their devices want to stream a specific content, it will hit the cache control service to get which OCA has that content which the user wants to stream, and then point the user to stream from the OCA which is closest to that user's device. As we just discussed, these open connect appliances or OCAs report health, etc. metrics along with available files that are cached with them to cache control service, or which they call as CCS, so that when a client requests to stream a certain video, the cache control service can provide details about which OCA to connect with. And if there is a OCMS or cache miss, similar to what we read above about read-through streaming cache on CDN, similar will be done here with OCA as well.